Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are studying the first module of this course, that is the introduction module. Within this module, my aim is to give you a basic understanding, basic introduction of what an operating system is and how does it work. So within this module, there is this topic computer hardware review, which we are going through. And in this topic, essentially, we are trying to understand how the computer hardware works. Before we actually formally go and study operating systems, it is important to study computer hardware, as I said in the previous video also, because the fundamental job of the operating system is to manage the computer hardware. And in order to understand how does an operating system do it, we have to have a good understanding of the computer hardware. So that is what we are going through. We are doing a brief review of the computer hardware concepts. So in the previous video, that is computer basics, I talked about what a computer is, what does it do, right? The very basics of a computer. Now, before I go into the individual components, that is the CPU, memory, and IO devices, the major components of a computer, before I talk about these individual components in more detail, in this video, we are going to study a much important topic, which is basically how we as humans can communicate with the computer. So the point is, the computer is an electronic device and it only understands electricity. So before we do any kind of computation, we need to have a way in which we humans can communicate with the computer. We humans basically talk in natural languages like English, French, Spanish, Hindi, which is very different from what a machine would understand. So that is what is the topic of this video. We are going to understand how we as humans can communicate with the machines. And the name of this video, The Big Boolean Theory, which is the same as the name of the channel, and it's a really peculiar name, but by the end of this video you will get the rationale of why the video and the channel is named The Big Boolean Theory. So let's get started. So I will start the discussion with this diagram, the von Neumann model that we studied in the previous video. So what does this model say? This model say that a computer takes the input from input devices, that input goes into the memory, and the input that the user gives essentially has two types, the instructions and the data. Now the CPU basically fetches those instructions and the data, executes those instructions to manipulate that data and produces some output data. That output data is sent to the output devices for the consumption of the user. So this is the overall flow of computation. But if you look closely, there is an important question that needs to be answered. So here in the memory, the contents of the memory, that is the instructions and the data, that is what this processor works upon. So first of all, we as humans must be able to express these instructions and data into something using something that the computer actually understands. What, like, we cannot just command the computer, it won't understand what we say, right? So first of all, we need to represent the instructions and data in the language of the computer. So let us first understand what is the language of the computer. So what does the computer understand? So the computer is an electronic device and it runs on electricity. So all it understands is the absence of electricity or the presence of electricity. The absence of electricity can be said to be an off state, and the presence of electricity can be described to be an on state, just like an electric bulb. So either there is electricity or there is not. The computer does not understand anything else, right? So how can we now represent all that we want using these two electronic states, that is on and off? So the first step that we take is that we can map these two states into two symbols. So basically the on state can be thought of as 1 and the off state can be thought of as 0. So these are just two symbols. We know them as numbers, but we can map these to the electronic states. So the point here is that the computer does not understand anything else, and we must be able to represent all the information that we want the computer to process for us using these two symbols. Also, not only the information, all kinds of computation also will now happen on these two symbols. So these two symbols are now basically a bridge between us and the computer. So let us now understand how we'll be able to accomplish all these using these two symbols. So to understand how can we do all sorts of things using these two symbols, let us go back to our basic school elementary mathematics. So if you look at mathematics, all of that is based on 10 symbols, and that we call as the decimal number system. So all the mathematics and in turn the sciences use this decimal number system to do the computation. So how does the decimal number system work? If we understand that, then we can extend the same idea to our number system of two symbols, that is 0 and 1s. So the decimal number system is a fairly simple. It has 10 symbols. We are all aware of it, from 0, 1, 2 till 9. And the name of the number system is derived from the term deci, and deci means 10. So the number system is named after the number of symbols that are there, unique symbols that are there in the number system. And every element, right, every unique element of the decimal number system is called the digit. So the number system with 10 symbols is called the decimal number system, and each of these symbol is known as the digit. Now using this same idea, let us extend that to our number system of two symbols, which the computer understands. So the number system with two symbols is called the binary number system. Just like the number system with 10 symbols derive the name from the term deci, here the name comes from the term bi, which means 2. And equivalently, the unique symbol in the binary number system is called the bit. So there are 2 bits in the binary number system, just like there are 10 digits in the decimal number system. Now that we know what is a binary number system, we basically have to work with this binary number system and represent all that we want, all kinds of information, and do all kinds of computation using this number system, so that the computer can understand what we want it to do. So let us now see how is that possible. Okay, so now let us understand how we will be able to do all of the things that we want using these two symbols, zeros and ones. So there are two parts to this. First of all, we have to represent all the information that we want, be it numbers, text, images, audio, video, everything that we deal with when we are basically dealing with computers, everything that we supply to the computer for it to process for us, every kind of information we should be able to represent that using this two symbols. So first part is the representation of information. And once we have a way in which we can represent all that we want using these two symbols, we also need a way to be able to perform the computation using these two symbols. So if you look at mathematics, it is not only about writing numbers using the decimal number system. Okay, you have a way to represent all the numbers, rational numbers, irrational numbers, negative, positive, all those numbers you are able to represent using the decimal number system. That is fine. But you also have this whole branch of arithmetic using which you know how to add those types of numbers, subtraction, multiplication. So every operation that we do on this, so all these also we should be able to do using the binary number system. So apart from representation of information, to be able to do the computation that we want the computer to do for us, everything we should be able to do using these two symbols. Mind you, we don't have the decimal number system now, so we must have a different system to deal with the arithmetic and logic operations of two symbols. So how can we do that? So the first part, that is the representation of information, it happens using the binary number system, and that we will see in this video later, how every kind of data, as I said, text, numbers, images, audio, video, we will see in this video how we can do that using the binary number system. So the number system helps us with that. The representation is taken care of by the number system. Once we have the representation of information, we also need the way to perform computation, and that comes from a branch of mathematics which we call Boolean algebra. So this Boolean algebra is a branch of mathematics which deals with the operations using two states, that we have 0 and 1. And why do we have this name Boolean, which is a very peculiar term? So the origin of this term is from the scientist who proposed this. So George Boole proposed this branch of science using which branch of mathematics using which we can perform the computation on two symbols. He basically proposed this for the purposes of logic, and he used true and false to propose his Boolean algebra, but all the ideas that he gave in that concept extend really well to the binary number system for as well. So the science of Boolean algebra basically deals with the computations, arithmetic and logic operations that we want to do with these two symbols, and those two symbols could be used to represent anything: the states of electricity, on, off, the states of logic, that is true, false, or just the numbers 0 and 1. You just have two symbols or two values, and how can we combine those two values to do all sorts of arithmetic and logic operations? That is given to us by Boolean algebra, which was proposed by George Boole. So now we know how can we represent the information, and we also know how can we do the computation. And once we have these two things, all that is needed is there. Now the computer can understand whatever we say using, because we have represented the information in binary number system, and whatever computation or processing we are asking the computer to do, it is only being done on two symbols, and there is Boolean algebra to help us out. So everything that the computer does, and whatever you see the modern computer being able to achieve, is done on top of just two symbols. And this idea is a very powerful idea. So just imagine everything that you do. You watch movies, then there is all sorts of images, web surfing, gaming, everything that you do is based on just two symbols. And this is a very powerful and beautiful idea in its own. And that is why the name of this channel I chose as the Big Boolean theory. So it's a big theory of computation that is based on Boolean, these two values, zeros and ones. So that is the rationale behind the name, the Big Boolean theory. And also this video is named after this theory as well. So now in this video, we are going to look at how we are able to represent all kinds of information using the binary number system, right? So once we are able to understand how each of these pieces of information, text, numbers, images, video, audio, and even instructions. So it's not only just data, we also need to represent instructions. So all of these we will see in this video. And once you understand this, you will be able to appreciate how the computer is able to do what it is able to do using just these two symbols, which in itself is a very powerful idea. So now let us start by understanding how can we represent the very basic information, that is first of all the numbers. If we are able to represent numbers, then the other things will become easier. So let us start by understanding how can we represent numbers using the binary number system, right? So to understand how we can do that, let us see how we are currently representing numbers using the decimal number system. So by numbers, I mean all the numbers on the number line, right? From minus infinity to infinity, all the possible numbers that we represent using the decimal number system. I am talking about that number line. So if you think about the decimal numbers, if you were only allowed to use one digit, one decimal, basically one digit, then what are all the possible numbers that you would be able to represent using decimal number system? So from 0 till 9, you're only allowed to use one digit, and that one digit you will fill with all the possible symbols in the decimal number system. So 10 numbers we can represent using one digit. Now let us say you are allowed to use two digits. Then as you can see, you can represent 100 numbers. So there are two places, and the first place we will fill with all the possible digits, and then again for all those combinations we will fill the first digit, the second digit again with all the 10 possible combinations. So you can see from 0 to 9 we go vertically, and we also go from 0 to 9 horizontally. So using two digits we are able to represent 100 numbers, 10 into 10, 10 to the power 2. So this is how we can extend this idea to multiple digits, 3 digits, and so on. And this table basically summarizes what I'm trying to say. So this is the first column, is the number of digits that we can use, and then the second column is the number of possible combinations of numbers that we can represent using these many digits. So for one digit there is 10 raised to 1, 10 possible combination that we just saw. For two digits there are 10 raised to the power 2, that is 100 possible combinations, which we saw in the previous slide. And then you can extend this idea to 3 up till whatever you number of digits you want to use. So there are some special units. For example, if you have 3 digits, then the number of combination is 1000 and we mark it as by 1000 or 1k, then if you have 6 digits, then you can represent 10 to the power 6, that is 1 million numbers. Similarly 1 billion and 1 trillion and so on. So this is how we can use the digits in different combinations, use different number of digits to get the different combinations and numbers. So now we will use the same idea to form numbers using the binary number system. So in the binary number system, we have two symbols, 1 and 0. 1 corresponds to the on state of electricity, that is presence of electricity, and 0 to the off state of electricity, that is the absence of electricity. And before we try to understand how can we form numbers using 0 and 1, we already know that the symbol, each symbol in the binary number system is called bit, and bit is also the term that is used to call the smallest unit of computer storage. So basically, if you talk about the computer and its storage, then the fundamental unit of storage is a bit, and you can store one symbol, one binary value in a bit. It could be either a 1 and 0, and all the storage that all the different forms of storage will be based on this bit. The point in this slide that I'm trying to make is that the smallest amount of information that you can store is 1 bit, and that bit is also used, the term bit is also used as the name for the smallest unit of computer storage. So now let us see how can we form the different numbers using bits. So just like we did for the decimal number system, let's say the question here is how many binary numbers you can create using 1 bit. So there are only two possible combinations, the 0 and 1, and we can map this to the decimal number 0 and 1. So if you want to represent the decimal number 0, we can do using the 1 bit 0, and if you want to represent the decimal number 1, you can just use the 1 bit and store the value of 1. So this was about using just 1 bit. Let's extend this idea in a similar way and use 2 bits. So how many possible combinations are there using 2 bits? It is just like the previous case, 2 into 2, it will be 4. So using these two places, try and make all the possible combinations. The first place can have either 0 or 1. Again, the second place can have either 0 and 1. And all the possible combinations are 2 into 2, 4. So 0, 0, 0, 1, 1, 0, 1, 1. And then we can map these combinations of bits to the decimal number system. So now we have 4 numbers in the decimal number system. Let me do this one more time. So now we'll try to make all the numbers that are possible using 3 bits. So 3 bits, we can make 2 into 2 into 2, that is 8. 2 to the power 3, we can make 8 possible combinations using 3 bits. Again, for every possible place, you can use either 0 and 1, and you can form all these possible combinations. And these combinations we can map to the decimal number system to get the number that we want to represent. So this is how we can represent numbers using the binary number system, using different possible combinations of bits. So this table summarizes how many numbers basically we can represent using using a certain number of bits. So the first column displays the number of bits that you want to use, and the second column is the number of possible combinations or the number of possible numbers that you will be able to represent using this certain number of bits. So we already saw for 1 there is 2, for 2 there is 4, for 3 there is 8, and the way we get this number is just compute 2 raised to the power of the number of bits that we want to use. And just like we saw in the decimal number system, there are some standard names for a certain number of bits. For example, if you use 10 bits, then the number of possible combination is 2 to the power 10 or 1024. This is a standard number, and it is given the num 1 kilo. For 2 to the power 20, it is 1 mega. For 2 to the power 30, it is 1 giga. And similarly, for 2 to the power 40, it is 1 tera. And you might have already heard these terms when you might have gone to buy some storage, right? If you want to go to buy some like DRAM or hard disk, then you get the storage capacity of this storage devices in these numbers. So megabytes or gigabytes in, so these numbers are used there also. So this is how many numbers that we can represent using the binary number system by using certain number of bits. So now the next thing that I want to talk about is that how can we convert the binary numbers into back to the decimal number system. So this is just a bit combination. So how you will be able to make sense of what decimal number this bit pattern is representing. So to understand this, let us take the example of how we do this in the decimal number system. So this is a pattern in the decimal number system, 4518. It's a sequence of some digits, but how do we make sense that it is 4518? It is just 4518, some sequence of decimal symbols. The way we make sense of what decimal number does this pattern represent is by basically each place has a certain weight. So the first place, the unit place, then there is the 10th place, 100th place, 1000th place. You must have seen this in your elementary school. So 8 has the weight of 1, and that can be represented as 10 to the power 0. So you multiply these, the symbol and the weight, and you get 8. So this 1 is basically on the 10th place. So the weight for this symbol, this place, is 10 to the power 1. You multiply this and you get 10. Similarly, for 5, it's on the 100th place, and the weight it has is 10 to the power 2 or 100, and you get 500. Similarly, you get for 4, it is 4000. You add all of this and then you get 4518. So this is how it is a weighted sum of the individual symbols. So in the same way, in the binary number system, if you are given a pattern, you have to perform a weighted sum. And what are the weights? In this case, the weight was the number of symbols in the number system to the power the position of this symbol. So here the number of symbols in the binary number system is 2. So instead of using 10, we will use 2, and the position remains the same. So this is how you get the weights. So just like 10 to the power 0 up till 10 to the power 3, the weights here will be 2 to the power 0 up till 2 to the power 3, and so on. So to get what decimal number or what number this bit pattern is representing, we do a weighted sum. So there are all these symbols 0, 1, 1, 0, and all the weights. You multiply 0 with 1, 1 with 2, 1 with 4, 0 with 8, and you add all of these 2 and 4, you get 6. And this is how we can get what number a particular bit pattern is representing by doing a weighted sum of the individual symbols in the bit pattern. So now let us look at an example. So here is a sequence of 8 bits. So for example, consider this is the state of some storage locations in the computer system. Now we have to make sense of what the computer system is currently storing. So we know that the absence of electricity is mapped to 0 and the presence of electricity is mapped to 1. So the number that that is being stored currently in the computer can be represented as 0110101. And now we can convert this bit pattern into the decimal number. For that, we will do the weighted sum. So what is the weight of each of these places? It's just the number of symbols in the binary number system, that is 2, with raised to the power of the position. So 0 up till 7. So we have the symbols, we have the weights, we will multiply each of them to get what each position is representing. So you have 1, 0, 0, 8, 0, 32, 64, and 0. And now we add all of these to get the number 108. So if basically what the slide is trying to say, if this is the state of storage in the computer system, if this is the state of electricity, then the number that we are representing is 108. And this is how we would be able to represent any number by converting it into binary number system within the computer using the on and off states. So another thing that I want to discuss is that a sequence of 8 bits is called a byte, and generally computer storage is measured in bytes, not in bits, because it is more convenient to do at the granularity of 8 bits, that is a byte. So whenever you go to buy memory or storage, you will hear these terms, the byte. So this was about how we can represent the numbers using the binary number system. And now let us look at how can we represent other pieces of information. The next thing that we will look at is characters. Okay, so let us now look at how can we represent characters, the English characters I'm talking about, using the binary number system. So the way it is done is by following a code that is called ASCII code. So let us now see what is this ASCII code. So this is a keyboard, and whenever you type in some press some button in the keyboard, a character is typed on the screen. So have you ever wondered how this thing gets done? So you're typing some characters. Basically, each of the buttons on the keyboard represents a character. So when you type press a button, then a signal is sent to the system, a computer system, and that signal is obviously a binary signal, that is electric signal that is composed of ones and zeros, which can be thought of as binary. So using a binary pattern, we can represent these characters in the computer system. So let us look at this in a little bit more detail. So to represent any character, we use 1 byte. So 1 byte is basically 8 bits, and 8 bits is sufficient to represent all the characters that we want to represent. So using 8 bits, recall how many possible binary combinations are there. So if you refer this table, if you were given 8 bits, then you can have 256, 2 raised to the power of 8 possible combinations. And using these 256 possible combinations of bit patterns, you can represent all the characters that you want. So let us see how that is done. So there is a code defined that is called ASCII code. It stands for American Standard Code for Information Interchange. So this standard defines how can we represent the character set using this 256 bit patterns. So let us visit this website. This is the standard website for ASCII code, and here you will see all the bit patterns mapped to certain characters. So this is the standard website for ASCII code, asciicode.com, and here you can go down and there is a list of all the characters, how the bit patterns are mapped to the characters. So let us first look at the simple ones that we can understand easily. If you see, the first column represents the decimal number, so it goes from 0 till 256, 255, sorry. So it goes from 0 to 255, and then the second column, not the second column, there is a column for the bit pattern. So this is the equivalent bit pattern for this decimal number, and then there is this symbol that it represents. So for example, the English characters from capital uppercase English characters from A till Z are represented using the bit pattern for 65 up till it goes to 90, and there is a description that is these are uppercase English letters. Then let us look at the lowercase. So the lowercase English letters are represented from 97 and it goes up till 122. So see, you can see there is a bit pattern for every character that we want to represent. Then let us go to the decimal numbers. So these are the decimal number symbols. So from 48 till 57, you have this decimal number symbols, the digits basically from 0 till 9. And apart from this, then there are special characters. For example, there is the number sign, dollar, percent, ampersand, single quote, and all of these you can see there are many more. Some of the symbols are visible, that can be basically you can type and there will be a visible character on the screen. Some of them are not visible. For example, there is this tab. So when you press a tab, the cursor will move, but you won't see a visible character on the screen, right? Then there is enter also. So using all these 255 numbers and this bit patterns, you can see how we are able to represent all the characters that we are interested in, that are there on the keyboard. So this is how we are able to represent the characters. And once we have the characters, we can represent any form of text, because text is just a sequence of characters. So we have numbers, we have characters, we also have text. Now let us move forward and look at some multimedia information types, for example, image, audio, and video. So let us now look at how can we represent media using the binary number system. So by media, I mean the image, video, and audio. So let us look at each of them one by one. So let us understand what is an image. So if you look at any computer image, basically an image is a grid of tiny units called pixels. So here is an example image of a forest and a tree. So if you zoom into a particular rectangular region, for example, and if you look very close, then the image, you can see there are individual units. These are small locations, and essentially what you can now understand is that the image is essentially a grid, a 2D grid, and each single location in the grid is called a pixel. The property of a pixel is that the pixel will have a single color, right? You can see many different colors in the image, but if you divide the image into a grid, then the individual locations of the grid will be the pixel, and each pixel has a single color. So this is how we represent images inside a computer. So to talk more about the pixel, for example, so these three images, right, they all are the image of one thing, that is a circle, a red circle. But depending on the number of pixels that are there in the image, the resolution, which the term resolution we often use, right, to quantify how sharp an image is. So if you use more pixels, you can see the picture will be sharper, and if you use lesser pixels, the image will be blurry types. So now you get the idea of a pixel. So first of all, any image is a collection of pixel, and each pixel will have a single color. So now let us now look at how can we represent the colors that a pixel has. So to explain, I have a simple example. Let us consider let's start with a black and white image. So as I said, an image will be a grid of pixels. So we have a simple heart, and the heart is in black color. So you can see it's a grid of pixels. And how can we basically now represent the colors? So as you might have figured it out, so on the right side, I have assigned the white color as 0 and the black color as 1. So if we know this matrix, if we know this grid of numbers of zeros and ones, we can figure out, okay, wherever there is a 0, fill it with white color, and wherever there is a 1, fill it with black color. So representing purely black and white images is straightforward. Just have 0 for one white and 1 for black, or it could be vice versa. So mind you, and when I say black and white image, there could be shades of gray also, but here in this example it is just two binary colors, that is purely white or purely black. So now let us look at how can we represent colorful images. So this was a simple one, it had only black and white. We have so many different colors. How can we represent a colorful image? So there is a theory called RGB color theory, and the theory, I won't go into much detail how it works and why it works, but the color theory says that every color can be obtained from a mixture of red, green and blue. So you see a color matrix, 3D color cube you can say, and on this color cube there are three axes: the red color, the green color and the blue color. And the RGB color theory says that you can get any color in this cube with a mixture of red, green and blue. Depending on how much red you are mixing, how much green you are mixing, and what quantity of blue you are using, you'll get a different color. So this is just one side of the cube. You can see a GIF, that is the cube is rotating, and you can see all the colors that we want can be represented using this cube. So once we have this cube, the point of this slide is that any color is now a set of three colors: some amount of red, some amount of green and some amount of blue. So in order to illustrate the RGB color theory, I'm going to show you a small demo. So let us come back to Microsoft PowerPoint, and let us say I want to fill some color into this black and white image. So for that, let me go to this option of shading, and here you will see more fill colors. And within this, if you go to the custom option, this displays you all the colors that are supported by Microsoft PowerPoint. And here basically there are all the colors, and here you can see the color model is RGB, and every color that you will select will have some red, green and blue. So currently the color that is selected is white. The value for white color is 255 for red, 255 for green, 255 for blue. If I vary this color and let's say I change this scale, you can see this value has now changed. It is now some green color, and as I move this pointer, you can see this RGB value is constantly changing. So, and if I take it to, let's say, black, it will become all zeros, and if I take it to white, it becomes all 255, 255, 255. So there are three characters, one for red, one for green and one for blue. The minimum value of a character is 0, the maximum value of a character is 255. So basically each byte will store some value between 0 and 255, and using that we are able to represent these colors, right? So this is how the RGB color theory works. You have given a color, you have to represent it using red, green and blue. Now the job of storing a color or representing a color is as simple as just storing three numbers, one for red, one for green and one for blue. So this slide shows you how we can represent a colorful image now. So this is again a colorful image, and it has been broken down into different pixels, and corresponding to this image we have three grids. Remember when we had a black and white image, there was only one grid, but now since for every pixel we need to store three values, one red, one green and one blue. So for every location in this, for every pixel in this image, we have three values, and this image can now be represented as a 2D grid, set of 2D grids, one for red, one for green and one for blue. And if we combine the values at any particular location, you will get the corresponding color of the pixel in the image. So this is how we can represent a colorful image. And once we have represented a image, we can get a video, because a video is just a sequence of images. Just like we got text from characters, getting video from images is as simple as having a sequence of images, right? So you can see one example here that there are multiple images drawn on paper, and this, when you play those sequence of images, it becomes a video. So this was about video. And finally, let's talk about audio. So audio is an analog signal, right? This, when you sample audio from any device, it generates an analog signal which looks like this wavy curve. So in order to store the audio, what we basically do, we sample this analog signal, this curve, at periodic intervals. So you can see this is the small interval, and we sample this audio signal via these blue points. At every periodic interval, we sample the audio values, and what we get is some number, and that number indicates the value of that signal. So essentially now the audio is a set of sampled points, and each point is just a number. So audio is again a sequence of signal values or numbers. So that is how we can represent audio. We saw image, we saw video, and we saw audio. Now basically you understand how we are able to represent any kind of media using the binary number system. Essentially we are relying on the numbers, and numbers can be represented using the bit patterns. So now we have seen how can we represent data. We saw numbers, then we saw characters, text, image, audio, video, right? We have seen many different types of data formats. So we have the data, we have a way to represent the data, but the von Neumann model, if you see it, there is not just data, we also need to represent the instructions. So now let us see how can we represent the instructions in the memory using the binary number system. So now we'll talk about representing instructions. So let us take a very simple example. We have a simple computer, and the computer only supports, let's say, 8 operation. It's a very hypothetical simple computer. It only supports 8 operation. What are the operations? These are basic arithmetic and logic operations, that is add, subtract, multiply, divide, logical not, logical and, logical or, and logical XOR. So these are 8 operations, and what we can do, we can assign a binary code, a bit pattern to each of these operations. So basically from 0 to 7 we have assigned 1-on-1 bit pattern to each operation. So whenever we give a particular bit pattern, the computer will know, okay, it has to now perform which operation. For example, if we have to do addition, we will provide the opcode of 0. So these are known as opcode or operation codes. And the set of operations that a computer can support is called the instruction set architecture. We will study about this term in the next video when we talk in detail about CPU. So now let us see how can we represent instructions. So here I have shown a simple example. These two are instructions. What is this instruction trying to say? It is trying to say perform the operation of addition on these two operands. What are the operands? There's decimal number 6 and decimal number 15. So we have already seen how can we represent numbers using binary bit patterns. So for example, 6 will be 0 1 1 0, 15 will be 1 1 1 1. So we need 4 bit patterns, 4 bits to represent these numbers. And finally here is we have the operation code. So operation code 0 is for add, and as we saw in this table, for multiply the operation code is 0 1 0. So 0 1 0 we substitute for multiply. So now when the computer sees this instruction, it can break it into 3 parts. It knows how to break it into parts. So the first 3 bits will be the operation that it has to perform. The next 4 bits will be the first operand, and the final 4, the last 4 bits will be the second operand. And in this way we can design multiple operations, multiple instruction types, but this simple example should give you a flavor of how these things work. So we will pass on this instruction, this sequence of bit pattern, and the computer knows how to figure out the operation code and the operands. This is how we can represent instructions using the binary number system. And here there is a simple example. So the instructions that we saw in the previous slide. So this is the CPU. The CPU, if you give the instruction add 615, if you give this bit pattern, it knows, okay, this is the operation that I have to perform, and the result you get is 15 plus 6, 21. Similarly, if you give this bit pattern, the computer knows, okay, this bit pattern means multiplication, so I have to add 6 with multiply 6 with 15, so the result is 90. So this is the sum and this is the product, and the operation result depends on the output that you provided. So this is how you can represent instructions in the computer system. So let us now come back to this slide. This slide was basically saying what all do we need to do anything with the computer. So the first part was we need to be able to represent information, and we saw many examples how can we represent information using the binary number system. So we started with numbers, then with numbers we represented characters, and from characters you can represent text. We also saw how can we represent images using numbers, and video using images, and also audio. And apart from data, we also saw how can we encode instructions using binary number system. So now we have all the things that we need to represent information in the system. We now need the way to how to perform computation. And as I said, that the theory of how can you perform computation using two symbols is given to us by Boolean algebra. So this is a branch of science in altogether, and I won't go into the details of Boolean algebra because it is out of the scope of this video. It will take another course to explain Boolean algebra. But again, you can study Boolean algebra from online courses. But the idea is there exists a branch of science which enables us to perform computation, that is arithmetic and logic operations using two symbols. So now we have the way to represent information. We also have a way to perform computation, and the computer is now ready to do the processing. It can do anything that it does, it can achieve anything that it does using just two symbols. And that is about the big Boolean theory that I wanted to discuss. So it's a big theory and it is all based on Boolean, the two values, zeros and ones. So guys, this was it for this video. Thank you very much for watching, and from the next video onwards we'll start looking at the individual hardware components. Now that we have a good understanding of how the computer understands what we want to say, let us now look in the next videos how the computer does what it does. So the next video will be about CPU. So this video, that was it for this video. Thanks again for watching, and I will meet you in the next video. Thank you.